Brazil. And he's going to be talking about theory and simulations of charge regulation of colloidal particles in electrolyte solutions. Thank you.
Okay, well, thank you for all coming here after lunch. Let's try not to fall asleep. Well, what I will talk about is something which usually in physics we don't take into account, because for us usually the charge is something that is given. And so if you have colloidal particles, we think the charge is fixed, and then we do the Levin-Theory theory or some other kind of theory. Same thing with proteins or polyelectrolytes. Usually we just think that the charge is fixed. However, in the real world, the charge is not fixed, and the charge really is a very strong function of pH and not so strong function of electrolyte concentration that we have in the suspensions. So this is basically what I will try to convey to you in this talk, is how can we treat charge regulation, basically how charges depend on the pH of suspensions or salt concentration, ionic strength inside of the suspension, and how this can affect the physical properties of suspensions also. So, but first let me tell you that this is the work which was done primarily with Amin, who is here and who is going to talk about some details of the simulations that I will discuss, and also the theory part was done with Thiago Colla and Derek Friedel. So Thiago is a professor at, so he was an ex-student of mine, so now, well, for a while now he has been a professor in Ouro Preto, and Amin now is a professor at Federal University of Rio Grande, and Derek is in Chile, in Santiago. pH. So we learn in high school that pH is basically given by the minus log base 10 of the concentration measured in moles. So there is a normalization here for the molar concentration. In reality, this is only an approximation. Okay, it's valid if we don't have salt inside the solution. So the pH, the correct definition of pH is not through the concentration, but through the activity. And the activity then takes into account all other interactions which exist inside the solution. So you have electrostatic interactions with all the other ions, and this affects the chemical potential, which in turn affects the activity. And of course, the pH scale then goes from 0 to 14, I mean, at least in the normal circumstance. And we say that something is acidic if the pH is below 7, and something is alkaline if it's above 7. And of course, pH is, I mean, in biology, everything is pH dependent. So if you change the pH, it can affect the growth of your plants. You can denature proteins. There is all kind of havoc that you can bring on your system if you just play around with pH. And partially this happens because pH controls the charges. So basically how many groups will stay protonated, how many groups will become deprotonated is completely controlled by the pH that you have inside the solution. So if you have acidic or basic groups, they will be strongly affected by the pH that you have inside the suspension. So a very long time ago now, there was a method which called constant pH simulations, which were introduced to try to account for how to treat the protonation, deprotonation reactions within the Monte Carlo simulations. So everybody here knows about the Monte Carlo simulation. So basically we try to sample the system with a Boltzmann probability. And so if it's just a simple Coulomb system where the charges are fixed, and we will just move the particles around, and then we will accept or reject the Monte Carlo moves based on the variation of the energy, and then we compare it. It's just a Boltzmann factor. And based on this Boltzmann factor, we will accept or reject the moves. Well, if we want to have protonation, deprotonation moves, where you can take a proton from interior of your suspension, which proton usually is in the form of the hydronium ion. So it's not just a single proton, it's usually stuck to a water molecule. But you have to transfer this proton to, say, a weak acidic group, or you take the proton which is on top of the weak acidic group and you put it in the contact with the water molecule, creating a hydronium ion. Then you can sample this kind of moves using this constant pH simulations, where this is basically the change in the energy of your system because you took a proton, say, from the bulk of water and put it on top of the surface group. This pH is what the pH of the bulk suspension is, and pK is the logarithm of the association constant for the reaction, where the proton is going to be associated with a acidic group. And here is the log 10, we'll see the nature of this log 10 basically comes because all things, the correct way to define activities in terms of the natural logarithm, while the pH traditionally has been defined through logarithm of base 10. So if we have a deprotonation moves, this parameter here will be if it takes a move or removes the proton or or put it back into the bulk, then this is going to be plus or minus 1. So this is very traditional. This was introduced, I think, 30, 40 years ago, when we really didn't have sufficient computer power to really simulate electrostatic interactions in all details. Basically, we didn't have explicit ions, so what you did is just said, okay, there is a screened interactions between all the particles, and the screening length is determined by Debye length, so you kind of already shoved a lot of theory into your simulation because you don't have explicit ions. And this works reasonably well, but then what people started to do is they try to change the system where you start to put real explicit ions. So the electrostatic now includes all the explicit ions that you have inside the system. The water you still model as a dielectric continuum. And they try to use the same algorithm. So what is the problem with that? Well, the problem is that the pH, if we go back to this equation here for the acceptance of the Monte Carlo move, it depends on the pH of the solution. If you look at this and you just rewrite pH as in terms of the activity, which is defined basically here, and activity, you have to remember, is just an exponential of base E of the chemical potential, then what you discover is that this term, really the nature of it is that it's like a chemical potential. So it's like a chemical potential. This is like an additional energy that you get the chemical energy because you form a bond, a covalent bond between the proton and your weak acidic residue. But it's really clear that if you just compare this to a grand canonical Monte Carlo, that this term looks like a chemical potential, and basically what you are doing is you are putting the system in contact with a reservoir in which you have the chemical potential, which is well controlled, it's defined, and then you are doing a Monte Carlo move where you remove a proton from the reservoir and you bring it towards the acidic or basic group on the surface, and the move is accepted or rejected. So the point is that this thing here is like a chemical potential, and this weight, this Boltzmann weight, corresponds not to canonical Boltzmann weight, but to the grand canonical Boltzmann weight, because there is a chemical potential in it. Well, electrostatic systems are very complicated in the sense that usually you cannot cut off the Coulomb interaction. So if you want to probe the infinite thermodynamic limit, where you have a very large systems, Of course, you cannot do it inside the Monte Carlo simulation, so what do? What you do is you usually take a box, a simulation box, in which you have your ions and protons, whatever, your polyelectrolyte molecules, and then you periodically reproduce this box. You make an infinite image, infinite number of replicas of this periodic box, which form kind of a crystal with the structure of your box as a base, as a unit crystal of the system. And then what happens? Well, you have to sum over all these replicas. And then the way to do it is what's called Ewald summation. So you use Ewald summation to sum this infinite replicas and calculate what is going to be the effective energy of the ion inside your simulation box. So in general, the system has to be charge neutral, because if you don't have charge neutrality, then of course, when you reproduce a simulation box which has an excess of, say, positive charge, you will have an infinitely charged positive crystal whose energy will just diverge. So people realized for a long time that to do properly the simulations, what you should do is treat the system as always neutral. So how do you do that? You don't make individual insertion moves. Say, I want to put a sodium ion inside the system. I cannot do it. What I should do is I combine the sodium ion with a chloride ion, and I make pair moves. So for the pair moves, then you have no problem, because at each Monte Carlo move, the system stays charge neutral. Okay? But there is still a problem, because I just finished telling you that this Boltzmann weight corresponds to the grand canonical ensemble and not a canonical ensemble. So in the grand canonical ensemble, what we actually have is we have a simulation box and we have a reservoir. A reservoir is separated from the simulation box. I mean, if we would do an experiment with the system, in reality, we would have something like this, where we have one side of the system where we have like colloidal particles or some polyelectrolyte and some microions, which can exchange with the reservoir here. So this is our reservoir. And to separate the two, we would have to put a semi-permeable membrane, which would allow the flux of ions here, but would not allow the passage of this macromolecule. Okay, if we do that, then what's going to happen is that because the microions can diffuse into this medium, what will happen is that some of them will diffuse here, and then we will establish an electric field across the membrane, which will produce what's called Donan potential. So in reality, when you have a system separated from a reservoir, you always end up with a Donan potential. So when we do the simulations, people often forget that there exists a Donan potential between the reservoir and the system, even so that the reservoir is treated implicitly, but there still exists a potential. So if we transfer an ion say from the reservoir into the system here, there is a Donan potential implicitly at the interface here. So if I would want to transfer the ion into the system, just for the grand canonical part of the algorithm where you put the ion from, So if you want to transfer the ion from the reservoir into the system, you have the usual grand canonical weight, where this is the excess chemical potential of the ion inside the reservoir. So this is controlled. This is the number of ions of a given type. This is the volume of our simulation box. This is the concentration of ions in the reservoir. And then what we really should be doing is we should be adding the Donan potential. So for each move here between the system and reservoir, the ion, when it enters into the system, it has to come through this interface here, which is implicit, but it has to be there. So the Donan potential is usually completely forgotten, and it's not usually a problem, because if we do a pair moves, when we bring a positive and negative particle, the combination of a pair move will actually make the Donan potential cancel out. So if I make a pair move and I combine the positive and negative particles in my pair moves, then for the positive I will have positive phi d, for the negative one I will have a negative one, and then if I do the product of the two, then this will cancel out. So what we can do is we can then perform pair moves where the ions are, in the protonation moves, will be coupled together. So if I move a proton from reservoir, for example, from the hydronium ion that is in the reservoir into the system, then this donor potential will cancel out, because I will combine this move with also bringing like a chloride ion into the system at the same time. And then the pair moves, for example, for the deprotonation and removal of an ion will give me this weight for the, and this one is going to be for protonation and adding a counter ion at the same time. So then we have this modification of that algorithm that I showed you before. And what we end up with is that if we want to do the deprotonation move where we remove a proton from the surface group and put it in the reservoir, then there is acceptance for this move, which is going to be given by this term. Remember that what we had before was in that CPH algorithm, we just had this part here. Now we actually have all this other part because we have to combine the deprotonation move with the removal of a positive ion as well. So in the end, what we have is this deprotonation and protonation moves, which are related to these factors, which are different than what the factors are in the CPH simulation. There is an additional subtlety when we talk about these types of simulations, is that if you go to the definition of the pH in chemistry, the pH is defined up to the uniform potential that exists inside the phase. So since I told you that there is a donor potential between the reservoir and the system, that means that the average potential inside the reservoir and the average potential inside the system will be different, and the pH has to account for this potential difference. So this is a subtlety. The pH is not electrochemical potential, because the electrochemical potential would be uniform throughout the system, but the pH is just defined up to the average potential that exists within the phase, and those will be different because of the existence of the donor potential. So if I do this kind of simulations, what I can calculate then is going to be the protonation state or deprotonation state of my colloidal particles of polyelectrolyte as a function of pH inside the reservoir and not as a function of pH inside the system. These two will be different by the presence of the donor potential. So this is how we should be doing the simulations, but again, this is not exactly what we want. What we really would like to know is what is the protonation state of the system as a function of pH, which exists inside the system and not in the reservoir. The two, again, are different. So this is our problem, and then what we need to do is, if we want to relate these two things, we need to define what we need to define is, or figure out a way to calculate the donor potential that exists between these two systems, between the reservoir and the colloidal suspension. So, let me see. So what we did is, I don't think I have a slide for that now. What we did is we introduced a different method where we calculate. What I told you before is that it's very complicated to make the protonation moves independently. That if we have to conserve, the total charge inside the system. So the way that it's done is to do the pair moves. What we did is we found a way to relax this and make the individual moves, but for example, if we make a move of bringing a sodium ion, which would then destroy the charge neutrality of your simulation cell, you have to put a uniform background to regularize the electrostatic potential of this infinite lattice. And then what we do is we self-consistently calculate what has to be the dominant potential, which acts as a Lagrange multiplier, basically to conserve the number of charges inside the system, and on average produce the charge neutrality in terms of just the ions without having the background. So it's a kind of a technical detail, but then if we do that, then we can calculate what is going to be the dominant potential between the reservoir and the system, and then if we know the dominant potentials, then we can calculate what is the pH both in the reservoir, which is fixed in the simulation, but then we can calculate what is going to be here. And this is how the experiments are usually done. Experiments are not done with a system that is contact with a reservoir of acid and salt. It's usually done on a closed system where you have colloidal particles and you have some ions here, and you change the pH by adding, say, hydrochloric acid to your suspension without having a membrane. But from the Monte Carlo simulation point of view, in this algorithm at least, we need to have the reservoir, and this is the analogous of CPH method, but this is the correct one. Okay, so this is not very convenient because we have to have the reservoir, we have to know what are the chemical potentials of all the ions inside the reservoir. So for a given concentration, you have to calculate what is going to be the chemical potential, because these are the parameters which enter into the grand canonical Monte Carlo. And this is really not very convenient because you have to do Widom particle insertion to calculate what is the chemical potential for a given concentration of salt and acid inside the reservoir to get all the chemical potentials, and then use those in this grand canonical simulation. So this is not very, very, very easy to do. For monovalent ions, it's not so bad because we can use a lot of approximations which exist, like mean spherical approximation or hypernetted chain, to calculate what are the chemical potentials are. But for multivalent ions, those approximations are not so good anymore, and if the ions have different radii, then it becomes very complicated. So what we did is, and we developed a different method, which we call canonical simulations, in this case, which also take into account the protonation and deprotonation moves, where the proton can come and associate with the surface group, or it can dissociate from the surface group and go into the bulk. So just to give you an idea how this thing goes about, so the usual canonical Boltzmann weight is given by this. So this is for the initial state where I have the proton inside the cell, and then I want to transfer this proton to the particle here. When I transfer the protons, and I remove the proton from the cell, so the number of protons that I have in the cell is going to be reduced. Okay, so the Boltzmann weight will be changed because of that. And then there is a gain in chemical energy because when I transfer the proton here, it forms a bound state with a surface group. And then there is a chemical energy associated with this bound state, which is just nothing more than the logarithm of the association constant, which you can think as 1 over the two-body partition function. And similarly, we can have for the deprotonation move, where we have this initial state, and then we go to this final state. So using the usual detailed balance argument, we can then derive the weights for acceptance of the deprotonation and protonation moves. So they are again dependent on the number of protons that I have inside the bulk of the system. So these are free protons. It depends on the association constant. So the association constant is just pure chemistry. You just go to the chemistry book and look what is the association constant for, say, carboxyl group for weak acidic groups that you're using, and the proton. So it's dissociation, association, reaction for very dilute systems. So this is just an input that we give to the system. And the electrostatic energy in this case is much simpler for us because everything, since we start with a charge neutral system, it stays charge neutral, so we don't have to include any neutralizing background. We just transfer from one part of the system into the other. Our proton, the total charge inside the system is automatically conserved. The problem with this algorithm, so this is the canonical simulation, it's very easy for us to calculate what is going to be the charge of the particle for a given number of for the total number of protons that I started with. So I take my simulation cell, I take off all the protons from the surface group, so all the groups of my polyelectrolyte are completely deprotonated. I throw these protons into the bulk, I throw the sodium, I throw the chloride. If I have calcium, I can put it all there, doesn't make any difference. And then I run the simulation, and the simulation will tell me how many of these protons will stay in the bulk and how many of them will become associated. So in the equilibrium state, I will calculate how many protons have adsorbed and how many will stay. The problem that I have is that this will only give me the charge that the particle will acquire in the equilibrium state as a function of the total number of protons. But I told you that the total number of protons are not directly associated with the pH of the solution. The pH is related to activity. And in systems with polyelectrolytes, we have very strong interactions between the particles. So approximating the activity by just concentration is a very bad thing to do. It doesn't work at all. So what we need to do is we need to find a way of calculating what is the pH of the system. So as I said, pH is related to the chemical potential of our protons inside the system. So if I know the chemical potential, then I can calculate what is going to be the pH. The problem is how to calculate the chemical potential. So the standard way to calculate the chemical potential is basically to do what's called Widom insertion, where I will take a virtual proton and I will try to stick it into the system, and some of these moves will be rejected with certain probability and some of them will be accepted. And based on this, I can calculate what is going to be the chemical potential. At least this way I can calculate what is the excess chemical potential. The difficulty is that what I need is not just the excess part. The excess part is related to the interaction part. I also need kind of the ideal gas part, the ideal part which is related to the entropic part, the purely entropic part. And that's related to the concentration. So the excess part takes care of the interactions, while the entropic part basically is related to the average concentration of the free protons that I will have inside the system. In general, for almost all the simulations, you find that the number of free protons that you have inside the system is extremely small because you cannot have very big simulation boxes. So in reality, you have very small concentration, and then you take logarithm of 0, and it gives you nonsense. So it doesn't work to do the normal Widom insertion to calculate what is the chemical potential of the proton. And this is why nobody ever does it. So we try to figure out, then, what can we do? Well, the idea is, okay, there are very few free protons, but there are lots of protons which are condensed on the surface groups of our polyelectrolyte or colloidal particle. So what we can do is, instead of sampling the protons in the bulk, trying to insert a virtual proton in the bulk, we can try to insert the virtual proton on the surface groups which are free. So if the surface group is already occupied by the proton, when we insert the virtual proton, this move is just going to be rejected. If it's free, then we can insert it and then see if this move is going to be accepted, and then we calculate basically this average here of the well, there is a subtlety here, which I will not enter, which is called the beta potential. Maybe Amin will mention a little bit more. This is just the electrostatic energy for inserting the proton. And then what we do is we calculate the average of this quantity here, and then we can calculate what is the pH. So this thing basically is related to the chemical potential, but instead of, so what we use is the fact that the chemical potential of the protons in the bulk and the protons which are associated with the surface charge groups has to be the same. So instead of probing what's going on in the bulk, we probe the surface, and this is the number of protons that we have associated after the equilibrium has been achieved. Z here is just the total number of surface groups. The pK is a logarithm of association constant for the surface group, which is again just pure chemistry, it's given. And then what we need to do is calculate this quantity here, and with this we can calculate what is going to be. With this we can calculate what is going to be the pH. So if we do this, then we can check really how bad is the CPH simulations are. Those original CPH simulations which with that simple weight where you have the pH minus pK that I showed right at the beginning of the talk, and you find that you have this green line here. And then if you use the canonical simulation that we developed, so then you get these points, you get this dashed line here. And if you use the grand canonical simulations, but corrected by calculating explicitly what is the Donan potential to take into account the difference between the potentials, the mean potential inside the reservoir and inside the system, and you calculate the correct pH inside the system, you find these points here. So you see these two simulations methods, the canonical and this grand canonical, agree perfectly, but the CPH method, which is usually what people use, is just completely off. Okay, so this is for 10 millimolar salt inside the suspension. You see that it just doesn't work at all, because if you compare the effective charge basically on your colloidal particles, there is a huge difference. For example, for this pH here, you get minus 200 here, and here you get like 150. So they're completely off. It's not just a few percent, it really is off. If we go to 100 millimolar salt, the CPH still does not work, but it's not so bad, but still there is a very large difference, because again, if you look in the vertical direction, you see that there is a lot of difference in the charge of your colloidal particles. And again, you see that canonical and the grand canonical simulations are in perfect agreement, while CPH does not work. Here, actually, for this very large salt, we know that there is going to be very small Donan potential. So as an additional test, what we actually did is we use the pair insertion, because we know that if there is a lot of salt, the Donan potential has to be very small. It's going to be negligible. And the pH in the reservoir has to be exactly the same as it's going to be inside the system. And then we see again that the pair points also fall on this curve. Here we couldn't have done this because there is a significant Donan potential, and pH would be different in the reservoir and with just pair potential simulations. With the pair insertion simulations, we wouldn't be able to calculate what is the pH inside the system. So we would only have the pH inside the reservoir, and here we plot the pH inside the system. So we couldn't use it in this case. But in this case, there is no problem, and we see that all three methods agree here, and they disagree from CPH simulation. So the bottom line is that one cannot use those simple CPH simulations. You really need to use O-pair insertion simulations if you are in the high salt, so in the biological context. It's fairly easy to use, at least if you have the chemical potentials of all your ions a priori, which usually you don't have. So you'll have to calculate, if you have calcium, you'll have to calculate what is the chemical potential of the calcium in the reservoir first, and then use that in the simulation. What I suggest is that it's much easier to do canonical simulation, because we don't have to worry about the peripotential, and then just use our surface Widom insertion to calculate what is the pH after the system equilibrated. But pure CPH simulations are not good. They don't work, and it's not controlled. I mean, we see that as we increase concentration of salt, it becomes less bad, but it's still bad. So one should try to avoid using this kind of approach. Okay, so this is the simulation methods. So now I pass to the theory. So what we wanted to do is, okay, so we can calculate the colloidal charge, basically, which will result from this protonation, deprotonation reactions at the surface. And what we would like to do is to see, can we predict theoretically what's going to be the number of condensed protons here, or protons which will be associated with the surface groups after the system equilibrates. So here we will start with a colloidal particle, so it has some surface groups, and we rip off all the protons, throw them in the simulation cell, put salt. If we have multivalent ions, we can put multivalent ions, because simulations can do whatever. And then what we would like to do is to see how many protons will get adsorbed to the surface groups after the equilibrium is established. Well, when we do the simulation, what we first observed is that actually the titration curve, so here's the titration curve, which is for a given salt concentration with vary pH, and what we see is that there is a titration, so at very low pH, almost all the groups are neutralized, so we have zero charge. Then as we increase pH, then we deprotonate a lot of surface groups, and finally we go to the bare charge, which would be the case where all the groups are completely deprotonated. So this is at very high pH, so there's no protons almost in this solution. And then we see that we saturate here at the effective charge. Well, what we observe first thing is that the titration curve seems to depend on the disorder of the surface groups. So if you want to do the kind of calculations, theoretical calculations, and in this case, we would have to somehow average over the disorder, and this is a real pain. So we don't want to do that. So what we did is we said, okay, what is the most regular arrangement of the surface sites on top of a sphere? And this is actually kind of a very old problem. It's called Thomson problem in electrostatics, of if you put charges on top of a sphere and you just let them anneal, then what's going to be the distribution of charges? So because you're on the surface, on a spherical surface, you cannot form a hexagonal crystal, which would be, in the planar case, what would be the minimum state. So you will have some defects, but in any case, if we do this kind of annealing procedure, we will find that, that locally, almost you see the hexagonal structure, but there are some defects, okay? But then with this kind of system, we don't have to average over the disorder. We get the most regular arrangements of the surface groups, and now we can do theory, because we don't have to worry about averaging over the disorder. So how do we do the theory? Well, so this is the structures that we get. So, most of these things are hexagonal, but if you look here, you'll find some pentagons. So the way that we're going to do the theory is we're going to say, okay, the effective charge, or the number of deprotonated groups which are going to be left on the surface, has to be related in this kind of two-state model, where the probability that the surface group is deprotonated is given by the Boltzmann factor, where this is the free energy for the system where the proton stays in the bulk. And for the protonated groups, then we'll have the Boltzmann weight, which is going to be given by this function here, where the F1 is going to be for the proton, which is on top of the surface group. And then our probability that the group is going to be deprotonated can be written just with usual normalization for the two-state problem by this Boltzmann weight here. Okay, so this is the free energy for the proton inside the bulk, and this is the free energy where the proton is on top of the surface group. So so if we just divide on top on the bottom by e to the minus beta phi 0, then what we find is that we can rewrite this expression as just in terms of the delta mu. And in this delta mu, then what will enter is we compare the two free energies. So in one case, the proton is in the bulk. So if the proton is in the bulk, it has the free energy, which is basically Gibbs free energy here, which is related to the chemical potential of the proton inside the bulk, so when it's far away from the colloidal surface. The colloidal surface is deproton, the site on which proton later on will condense, in this case, is deprotonated, and there is a certain what's called solvation free energy, which is associated with it, because if I have a charge inside an electrolyte, it's going to be screened by the electrolyte, and there is certain electrostatic free energy associated with that. Okay, so this is the initial state where the proton is in the bulk. The final state where the proton is going to be adsorbed to the surface. When it's adsorbed, then it gains the chemical energy. Again, this chemical energy is nothing more than the log of the reaction constant here, Ka. And it also gains an electrostatic energy from the interactions with all the other sides. So this is the potential that the proton will feel when it sits on top of the side and it interacts with all the other protons inside the system, with all the sodium and chloride ions or whatever other ions, and with all the other surface groups. So this is a total electrostatic potential that proton feels. I think this pointer is getting weak. Okay, so if we just take this, subtract these two terms, what we find is exactly this thing here, and then I can take this and rewrite this in terms of pKa, remembering our definition of pKa in terms of log base 10, so I will just rewrite that. This term here, after sticking it in here, and this is the pH, which is going to be related to the chemical potential of the proton in the bulk. And then there's these two terms here. The solvation free energy of the site can be neglected. For now, it's very small. And then we have this exponential of the surface potential. So this is not good. Okay, so what we need to do is, if we would know what is this potential is, what is the surface potential is, then in principle we could calculate the number of deprotonated groups that we have inside the system. The difficulty is that we don't know what the surface potential is, because the surface potential is going to be determined by all the other ions inside the system, plus how many of the surface groups are deprotonated. So this is the difficulty. So what we have to do is we have to calculate what is going to be the surface potential. And this is the real difficulty. Usually what people do is they say, okay, let's just take our surface groups, we just smear them all over the surface uniformly, and then I will have a surface which is going to be uniformly charged. And then if I take this charge, solve the Poisson-Boltzmann equation with that charge, and do everything self-consistently, I can solve the Poisson-Boltzmann equation self-consistently with this boundary condition, which is give me the surface charge density for the uniform distribution, completely smeared up the surface groups, that I can find what is going to be the effective charge. The difficulty with that kind of approach, and we see that in the simulation, is that it's not good. The problem is, it's okay to smear out the surface groups over the surface and neglect the discrete nature of the surface charges far away from the surface, because the electric field decays very fast away from the surface, and the discreteness effects basically just disappear. They go exponentially with the separation between the surface groups. So the discreteness effects in the bulk of the solution are completely irrelevant. If I want to calculate what is the potential say, 7 angstroms away from the surface, I can forget about the discreteness effect and just calculate the average surface charge, and everything will be okay. But if I look at the proton, which sits right on top of the surface, there is no screening around it, because the electric field can pass through the colloidal particle, and the surface effects, the discreteness effects, are very strong. So I cannot do this kind of approach where I just do the complete mean field. So what we do is we split the potential, this electrostatic potential, into the mean field contribution and the discreteness contribution. How do we in practice do it? You can add and subtract a uniform background. Then this discreteness effect would correspond to the background plus the surface groups, electrostatic potential produced by uniform sphere, basically, of charge equal to the total number of groups with the point charges of opposite sign. So it's kind of like one component plasma in the crystalline state. So this would be our potential for the one component plasma. And then this would be the minus of the background, which is exactly would be the mean field potential, which we would get if we didn't have any discreteness effects. So the discreteness effects, I can use the theory of one component plasma in the crystalline state, and I can calculate basically that the discreteness is going to be related to the total number of deprotonated groups. This is the total number of groups that I have on the surface. This is the Magellan constant for a hexagonal lattice. As I said, we can neglect basically the defects on this, topological defects on the sphere, and so we can use the constant for the hexagonal lattice. And lambda b is what's called the Bjerrum length, which is just depends on the dielectric constant of the medium. So in our case, it's water, so we take it to be 7.2 angstroms. So if we know this, again, the discreteness we could calculate, and then what's left over is to calculate what is mean field part. And to get that, what we do is we solve the Poisson equation. And the way that we do it in this case, we think, okay, I have a colloidal particle. I will put it inside a spherical cell. And the radius of this spherical cell in which this colloidal particle sits at the center is going to be related to the volume fraction of colloidal particles inside the suspension. Okay, so everything becomes spherically symmetric, so I integrate the Poisson equation, and this is going to be the result. Of course, the densities of all the electrostatic species, so here I have the species of type I. This is the valence of this species, for example. So if I have calcium, then Z would be 2. Sulfate, it would be -2. So there is I have to know what is the distribution of ions around, and the point is that the distribution of ions themselves is related. The distribution of ions is related to the Boltzmann factor of the mean field potential. So this is kind of like a Poisson-Boltzmann equation. What we do is, in addition to the mean field part, we also add the correlational part, because what we want to do is also apply this theory to say, sulfate ions, which have valence of -2, and then the correlational effects become important, so we have to add a contribution which comes from the correlations. But in any case, with this kind of approach, we can calculate what is the activity. So the activity is just the chemical potential inside the system. Note that this chemical potential is uniform inside the system, so it has to be by the definition. So the total chemical potential is uniform. So if I take the total chemical potential, do the exponential of it, rewrite it, I will get the activity, and then we see that the activity can actually be written in terms of this normalization factor, which is nothing more because we have a canonical system. So this is a total number of particles of type I that I have inside the cell, which is going to be normalized by this. So this is just a normalization. So what we find is the activity is related not to the average potential, but kind of weighted average of the distribution of ions inside the cell. And then the pH would be just calculated this way here. So if we know this, we get the pH. Okay, so the correlational part, and I don't want to go into the details of that, and we solve for the correlations. The point is that if you have, I mean, there is an additional repulsion. So imagine you have a hard wall and you have a charged particle. So in the bulk, this charged particle is completely screened by the counter ions. So there are all kinds of ions, positive and negative. So let's say I have sodium. I look at the sodium. There is an excess of chloride close to it, and then there is sodium. If you look at this, basically the interaction away from the sodium, so I fix it at 0 and look away from it, what I will find is that the electrostatic potential just decays exponentially, and this is the perfect debye screening. As I move the sodium toward the surface, what's going to happen? The screening atmosphere around the sodium ion is going to be perturbed because you broke the spherical symmetry that exists in the bulk because you have an interface here. So it's not going to be as happy going to the surface because its electric field is not going to be screened. There is electrostatic penalties and for it to be close to the surface because it's just not going to be able to get its self-energy screened. If you take this and, I mean, actually do the calculations, what you find is that you end up with this kind of potential for the interaction, which is a correlation-induced interaction because you break in the symmetry near the surface. So we can calculate this and just add the whole thing and put this into that Poisson-Boltzmann equation coupled with the boundary condition at the surface, this charge regulation boundary condition which I derived for this Z effective, and then we compare it to the simulations, and then we see, and actually I did it for 1,2 electrolyte, because for 1,1 electrolyte it's not so surprising that I mean, this theory works, and we saw it before that it was working well. But what was surprising is that if we take into account this correlation effects, then we actually see that, so this is a titration isotherm where we look at the effective charge, the surface charge density as a function of pH on a colloidal particle, and we see that it works very well. I mean, the agreement between the theory and simulation is perfect. And there are no adjustable parameters here. I mean, we didn't adjust anything at all. So we see this in that the theory is working well. We can also use the series and to calculate what is the density profiles of the counter ions, so the ions which have the charge opposite to the surface groups which are negatively charged in our case, and co-ions here, which are divalent here in this case. And we see that the density profiles are also perfectly described. This depletion here happens exactly because of that effect that I just described for the correlations, because we are modeling the suspension as being a colloidal particle which sits in the cell, and there is a hard wall at the boundary of that cell, which is, then we don't have to use the Ewald summation, we can just use usual Coulomb interactions. So in this case, we see that everything works perfectly well. So the conclusion, so time is up, perfect. Okay, so the conclusions, so we see that if we use Dawn and pair or canonical simulations in the regimes where they're supposed to work, they all agree between themselves. So we see that the method that we developed really works for calculating the charges and the protonation-deprotonation reaction. And there is nothing special about colloidal particles. We could do it for polyelectrolytes, or if you want to do proteins which have positive acidic and basic residues, you can also use it for that. I mean, there's really no, in principle, nothing special. So canonical titration can be performed easily. That's not surprising. We can do the canonical titration. What was the hindrance for using that method was that there was no way to relate the concentrations that you observe of the protons, which are very low in the bulk, to the pH of the system. And using this Widom insertion method that we developed, then you can actually calculate what is the pH, so it becomes much easier. You don't have to calculate a priori what are the chemical potentials of everything to do the simulations like you would have to do if you use the Donan or the Spear method that I described, which are intrinsically grand canonical. Here, we just use canonical simulation, and at the end, after the system has equilibrated, we just take and use the virtual particle insertion on the surface to probe what is going to be the pH of the final state, the equilibrium state. And finally, there are serious problems with the CPH algorithm, and it really shouldn't be used for simulations of systems in which we have explicit ions. Okay, so here, I'll stop here.
Thanks a lot, Jan. So we have time for questions now. I do have one myself, so anyone? Okay. What happens if the colloidal particle is not spherical? Because you mentioned radial symmetry at some point.
Yeah. Well, for theory part, we had to use the spherical particles. Otherwise, we cannot solve. I mean, you could combine this. There are packages like COMSOL or whatever that solve things for you. The only way that what you would need to do is somehow to include the boundary condition, this thing here, or the surface. Yeah, so this thing here. So this becomes kind of a boundary condition at the surface. So it's self-consistent boundary condition which relates the surface charge, which you don't know a priori because it has to be determined by the equilibrium, to the surface potential, which you also don't know, and then you close all these equations with the Poisson-Boltzmann equation. So for us to solve it, I mean, or semi-analytically, because it becomes simple, we can use for spherical symmetry, it becomes simple. We can do it for spherical symmetry. For cylindrical symmetry, probably we can also do it. But if you want to have like a protein or polyelectrolyte, which has very complicated form, and the form of the ion, polyelectrolyte, would also self-consistent. So imagine you have a polyelectrolyte which is completely deprotonated. So because of the repulsion between the monomers, it becomes very stretched. But now you start changing the pH, and many of the surface group become protonated, and then the charge goes down, and then this thing becomes more like a coil. So the form of your polyelectrolyte will be coupled to the charge state of the, so you would have to solve everything self-consistently, and that's impossible. So in that case, you really need to do just the simulations. The part of the simulations has nothing to do with, you can just given a sequence, let's say you have acidic and basic groups, and you know which one is which, and you just want to do the protonation, it's the same algorithm. There's nothing special. You just have to add what is the energy of your, for the bending energy of your polyelectrolyte, whatever. So you just will be part of the total energy, and then you just do the protonation, deprotonation move, and then the whole system will self-consistently equilibrate, and you will know what is the radius of gyration of in the final state as a function of pH and everything. But for the theory, no. For the theory, we really have to work with simple geometries. But what we wanted to know is basically how important are the surface effects, because there are lots of old theories. So this stuff, this approximation that I told you before, which is called Needham-Persegyan theory, where they take this potential and just treat it as a mean field potential, completely neglecting the discreteness of surface groups. In that case, there are old solutions of this thing for you can solve numerically also. I don't think there are exact solutions. But in any case, you can calculate the charge, but it's just wrong. It's not agrees with the simulations. So this is the point. Before there weren't really good simulations, because if you compare with the CPH simulations, then you have to twitch something. You will say that, okay, there's different pK, whatever, and then you just try to fit it to the theory. But in our case, when we compare theory and simulations, we use exactly the same pK. We use exactly the same number of protons, the same number of sodium, same number of... So the simulation is an exact solution of the model. And this is an approximate solution of the same model with exactly the same parameters, same radii of ions, same everything. So the simulation is an exact solution, and then we can see really that if you don't account for the discreteness effects correctly with with this term here. So then you end up with incorrect predictions for the effective charge of your particles or for polyelectrolytes.
If the surface was had a rugosity, would it change anything?
If what?
If the surface had a rugosity?
Well, again, for theory, I wouldn't know how to do that. I mean, I'd have to. I mean, the theory would become very complicated. Again, maybe combining this with some package, which, you know, because people solve these things for very complicated, Poisson-Boltzmann equation, you can solve for very complicated geometries. Numerically, I mean, you use the over-relaxation method or whatever. I try to stay away from, you know, from these things because I want to understand more the theory part, not so much the engineering part of what is the exact potential or whatever. So for this is the reason why we never try to do that. But if you have a good package and you know how to solve things numerically, all you have to do is, because the discreteness effects, I mean, if you have any surface, as long as the charge is more or less, the surface groups are more or less uniformly distributed on the surface with kind of this pseudo-hexagonal, then you could use exactly the same the same logic to account for the discreteness effect, and then you just combine it with a very complicated part for the mean field potential, which you would solve self-consistently from. But I mean, you could do it. I mean, but we didn't.
Oh, great job.
When you show these constant PhD simulations, do you compare with the experimental results or data?
No, this is the point. I mean, it's very difficult to compare with experimental results because you don't have the control over things, so you don't know. So what people do usually, I have a PK. The PK I know for the bulk reaction, so I have carboxyl interacting with hydronium. I can calculate what is, or measure what is the PK. But now you take carboxyl group and you put it on top of a surface where you break the symmetry, basically. The carboxyl stuck to the hard wall. Then PK is not going to be exactly the same. So people say, okay, so we will just adjust the PK, and then you compare things with by adjusting PK. So, but at each, for each different situation, you will just keep changing your PK, and that's not very, very satisfying. So you don't see that the CPH simulation does not work unless you compare it to the correct method. And what I'm saying is the correct method is to do either canonical simulation, like we did, or the complete grand canonical simulation in which you can calculate, but not the normal pair insertion, because the pair insertion will not give you the pH inside the system. You don't know what the chemical potential of ions inside the system. So basically, you need to compare to something that you are 100% sure that is correct. And this is what our simulations do. We know 100% that those simulations are correct, and then we can judge if there is a problem. The difficulty with so if we go back to the CPH simulation, so what you see is that somehow the CPH is really, they want to treat it as a canonical simulation, but the weight that they use is a grand canonical weight. So they want to say, no, I have a fixed number of protons inside my simulation box, because they never refer to the reservoir in this case. But the protonation is going to be somehow determined by pH. But the pH, you can only control the chemical potential inside the reservoir. As you do the simulation, your pH is changing inside the system. So if you have a canonical simulation, you start with something, you have all the protons taken out, put them in the bulk, you will have a very high or very low pH. Then as system equilibrates and goes to an equilibrium state, the pH will change completely. It's not going to be the same as. So, But in this simulation, you could somehow say that, no, we're going to fix the pH. So the idea was that you can fix the pH inside the system. But if you fix the pH inside the system, you cannot do that. You can only fix the pH, like in the grand canonical simulation. You fix the pH in the reservoir, and inside the system you have to, you would have the equilibrium, which will determine the number of ions that you will have because of the fixed pH. And you cannot fix both the number and the chemical potential in the same simulation. And this is basically what this kind of approaches try to do. And the problem appears when you want to take into account the electrostatic part. Yeah.
Thank you very much for your talk. I have a question. Is ion pairing playing a role in your phenomena, in what you are studying, and whether your theory is taking this into account?
Well, in this case, I mean, since we only looked at the sulfate ions. So they're divalent, so we have 1, 2 electrolytes. So the ion pairing in water at room temperature is not very strong for these things. If we would go to trivalent ions, yes, we would start having problems because you would start having barium pairs and things like that. But not in this case here. So much in the theory we don't include the pairs in this case. I mean, we don't account for that. So it's
because in some solvents you do have.
Oh yeah, if we would go to very low dielectric solvents, but here we are in water, so water is
Okay, so
it's 80. So
because I was thinking of experiments with charged colloids in solvents, then you do have ion pairings.
Well, it depends. I mean, if your solvent is water, then you don't have. But you could go in the low dielectric solvents. Then you would have pairing. Yes.
Okay.
Yeah.
Okay.
In principle, I mean, the simulation part wouldn't be affected by that because, I mean, the simulation takes care of everything because we calculate exactly the electrostatics in the simulation. So the energy is calculated exactly. In theory, what you can do is, actually we did a long time ago because there is a lot of work on overcharging or charge reversal of colloidal particles when you have like 3,1 electrolyte or something like that. In that case, you really need to worry about the pair formations. And then what you can do is you can kind of use the theory, like barium pair formation theory, which you can modify to have higher order clusters. And then you can combine it with Poisson-Boltzmann. So besides having just bare ions, you can also have clusters which you can self-consistently include in the theory. So we did this a long time ago. And it works fairly well. I mean, we never tried it with a charge regulation, but for just fixed surface charge, it worked well.
Thank you.
Thanks for the nice talk. I just wondering, you said that we need to have zero net charge on our system for apply this kind of method, if I understand correctly, because of the long-range nature of the electrostatic interaction. So to have a thermodynamic limit with finite energy. But if we do have net charge in our system, what can we do?
Well, I mean, what you have usually is a net charge. There is, if you think about what happens if you have a system and a reservoir, you will have some diffusion of ions, but the charge, and this is what produces the Donon potential. Basically, you have, let's say, you have a colloidal particle which is negatively charged. So you have a positive counter ions. And these positive counter ions can diffuse because they're small. Some of them will move into the, let's say, just colloidal suspension and water. So the water is separated from colloidal suspension by a semi-permeable membrane. So your positive ions then can drift across the membrane, and this will establish the potential difference across the membrane. Basically, you will have electric field, which will oppose the further drifting of the. But the amount of charge that has to go to the other side to produce a finite potential is actually very small compared to the total charge, total number of ions that you have in the system. So in this kind of, when you do the simulations, you never worry about, I mean, like in our case, when we do this modified grand canonical simulations where we allow violation of the charge neutrality, what we do is to calculate the electrostatic part, because you need to use the Ebald summation. You have to introduce like a uniform background. So it's a mathematical trick that you have to do to make everything converge. But then what you do is you have also a Donan potential, which is basically a Lagrange multiplier, which says that the total charge in terms of ions without a background has to cancel out inside the system. So you drive the system with a Donan potential to go to the state where the total charge inside the system is zero without a background. And you see that there is going to be finite Donan potential established. So Donan potential is kind of like a Lagrange multiplier to preserve the charge neutrality inside the cell. But physically, the Donan potential arises from this diffusion across the membrane.
Okay, thank you.
Okay, so let's thank Ian again.